Hey guys, today I'm gonna go over the current Division 3 contest and I'll try to explain my solutions along the way. I'm a bit late for the contest, but it doesn't really matter because it doesn't affect my rating. And even if it did affect my rating, I wouldn't be in that big of a trouble. Alright. In the pet store on sale there are A packs of dog food, B packs of cat food, C packs of universal food. X has eggs, Polycarp has eggs, dogs, Y cats. Is it possible he will be able to buy food for all of his animals? Okay. A, B, C, D, A, B, C, X, Y. Well, I will have, are there test cases? Yeah. A, B, C, X, Y. The difference is minimum of 0, A minus X minus A plus min 0 Y minus B is smaller than or equal to C, then yes, otherwise no. What if I don't even test this, just submit? Yeah, that sounds like fun. Represent contests. Oh, it shouldn't be min, it should be max. Eggs, dogs, okay. Here you have to be careful to submit again because it uploads it, not simply selects a path. See, there you go, you shouldn't test your code because you might get accepted on the first try, saving valuable seconds. Okay. Problem B, make it increasing. It's a problem title that appears almost in every contest. Or make it decreasing. So given n integers, you can perform the following operation on them. Select any element AI and divide it by 2. Okay, truncated. In other words, you can, okay. It becomes strictly increasing. Well, I can, oh, there are only 30 elements, that's stupid. But all I need to do, obviously, and this could be done for much more elements, up to like 10 to the 5th element, is go from the last element to the first element and make it increasing one by one, and each element I divide at most log n times. Yeah, but the length will be at most 30 if I divide all of the elements by at least 2 because it doubles each. Yeah, maybe it's good that n is equal to 30. Okay. While AI is bigger than AI plus 1, AI div equals to AI is bigger than or equal to, then I'll divide by 2. If AI equals AI minus 1, not minus 1 but plus 1, then OK equals 0. Yes. No. Oh, it's not yes, no, it's the minimum number of moves. Oh. Okay. I think this will also give me the minimum number of operations, so south minus 1. Okay, I'll test this because I'm not sure. I'll have to prove that when I'm in the explanation part, because I'm not sure why that's correct, but it's sort of, I have an idea. Okay. All right, problem C. Bought a new expensive painting and decided to show it to his N friends. He hung it in his room. N of his friends entered and exited there one by one. At one moment there was no more than one person in the room. Okay. Okay, so we have to find which friend took the painting. Polycarp asked his friends one by one. He asked each if there was a picture. When he entered the room, each friend answered one of 3 ways. No, yes, and can't remember. Did his friends go in and out in order? The first friend, then the second, and so on. So I think it's ordered. The ith friend, yeah. So what it's gonna look like is a bunch of 1s, then a bunch of 0s. Right, and in the third one, why is it only 2? Cannot. So what could happen is that, yeah, the one after the thief, so before the thief everyone has to have 0, I mean everyone has to have question mark or 1, and after the thief everyone has to have 0 or question mark. Two, 3, 4 on the 4th test case. Yeah, all of these are good. Okay, well I'll store this in some sort of prefix and that should work. And what I'm gonna do is I have a sub 0 and plus of n plus 1, and I'll have pref of, no, pref 1 of n plus 1. F1 I equals 1 if Si is not equal to 0. And I do the same thing but here it's n minus 1 bigger or equal to 0 and I answer I, and it cannot be 1. There's probably a sum function, but and I need to compile C. Okay, I'll try this one out. 1 1 2 5 4 1 1 3. Yeah, I just took a break because my food was ready, and that's why 1 hour disappeared. Well, 45 minutes, but close to an hour. Yeah. This might actually get difficult because not many people are solving G. Well, okay, they are, but I want to see. Well, there's purple who solved it, so might not be that hard. Okay. Anyway, we're on problem D. You are given a rooted tree consisting of n vertices. Vertices are numbered from 1 to n. Any vertex can be the root of the tree. But I am given the root of the tree. Right? Okay. A tree is a connect. Okay. And okay. The parent of a vertex U is a vertex that is the next vertex on the, okay, for, yeah. Okay, find such a set of paths that each vertex belongs to exactly one path. Each path can contain one or more vertices. In each path, the next level is son of the current vertex. Well, what else would happen? Right? Oh, I cannot have loops. I can just okay, so I think it's gonna be the number of, do I need to give the paths or only the number of paths? I'm gonna need a path per children, and then I can just do like, yeah, okay, that's gonna be some implementation. So I have these parent pointers. I need to have like leaf for int I equals 0, y smaller. From 1 to n, I read in its parent. And I increase the children of children plus n plus 1 zeros. If children I equals 0, leave pushback I. And I also need a visited of n. What? So I have an array visited. I go through all of the leaves for int so first I print out the number of paths. It's gonna be the number of leaves. I have okay. Okay, that should be it. Let's do the extra so that it's more visible. What? It splits the first one into 6 paths. Hmm. Five. The first node is 3. Second node is 1. For the 3, there should be 3 children, but it says there are 6 children. I mean, leaves. Okay, it's 2, 4, 5. Oh, that's the input. Okay, I'm down. I get it now. Two, 1, 3, 1, 5. And it always has to go downwards, so I think I need to reverse. That's why a stack would have been better for this. Okay. Wrong answer on test 1. Yeah, unless one, is it 1, 1, 1? That's the only case that I have not considered. 1 is 1, 1, 1, yeah. Whoa, that's a lot of 1s. And equals 1, count 1, 1, 1. Okay, what? Oh, because let's read and everything, and here do the 1, 1, 1, 1. Okay. Oh yeah, there's easier ways to code that, but it's good enough. enough. So let's look at our problem E, but I think I'll go get some water first. Okay, so problem E. Given a string S of lowercase Latin letters, or letters of the English alphabet, following operation can be used. Select one character from A to Z that occurs at least once in the string, and replace all such characters in the string with the previous one in alphabetical order on the loop. So A with Z, B with C with B, yeah. You are given the integer k, the maximum number of operations that can be performed. Find the minimum lexicographically possible string that can be obtained by performing no more than k operations. Well, that's easy enough. I go string character by character. I look at the first character and I turn it back as many times as possible. Then I look at the second character. And I always have to check what the mapping is of characters. I'm never gonna need to go around in a loop because I just need to get all of the characters down to A. And I have to print out the string. Okay, that's easy enough. So I have N and K. I'm gonna need at most 26 squared operations. Oh, it's not. Because here I first put C to B, and then I turn all B's into A's. Okay, that's interesting, because this means practically that what I can do is if I have some letter D, then I do D, C, B, A. In 4 moves, I can take all the characters that are D or lower and turn it into A. Okay, next strategy, I check the first character and I bring it down to A. Then let's say after this I see a B, well that has been also put down to A. Then I have CC and then I have a E. Let's say then I have an F and an E. Well, I know F hasn't been done yet. So in two operations I can decrease F down to A. In one operation I can decrease it to E. I store the largest character that has been decreased to A. I just store like a map of all the characters. Okay. And let's do this. I have int map of 26 iota mp plus 26 0, and then what I do is I could use this join set union, and that might make things easier. And I store a minimum for each set. Okay. If the parent of u is what? Ah, I shouldn't be confused about this. Yeah. Okay, that should work. Okay, I go through the characters. Vial is bigger than 0 and k. And next I go a plus mn of find yeah. Yeah, it should be a character. Maybe he doesn't know that. Okay, well, first of all, this didn't really do anything. Hmm. Hmm. First I unite it worked, but interesting. That I cannot use minus minus like that. But that got accepted. Solving it nice and slow. Okay, things that he has to do before coming to Nastya. So of course he's gonna start in X, do all of A in some order, and finish in Y. I will root the tree at X and do some sort of DFS. I need to store which subtree Nastya is in. Nestia. Don't know how to pronounce it. Nastya. Right, because here's what I'm thinking. Here's X, and it has a bunch of subtrees. And let's say this is y, and this also has a bunch of subtrees. Okay, so first I walk down here, finish this subtree optimally, walk up, down, finish optimally, up, and then I go down here towards Nastia. Down, up, down. When I've arrived at y, down, up, up. So first I'm gonna do in all subtrees, I'm gonna store whether y is in that subtree and whether I need to do a job in that subtree. And when I'm in a subtree like this where y isn't anywhere, okay. I think I'll implement F quickly and I'll leave G because I want to also explain the problems and upload it in time and stuff. Does that mean, yeah, I'm at about 50 minutes, so I have in sub I have so is it used and used and is enough because originally it doesn't stand for subtrees but it will, and I have y in, I have x and y, okay, and I have n and k. First of all I n k, then x, then y, then for int I equals 0 I smaller k plus plus I read in and used, okay, then I do a DFS x, that's a DFS1, if v does not equal p, used u used v, y in u or equals y in v, and y in y equals 1. And I'm gonna DFS v EU. Okay, and then I have void DFS2. Bool is y equals 0. If y in v, if v equals p, then I continue. Yeah, I think I'll do this here. If v is p, then that's ruled out. If y in v is y equals 1, y direction equals -1 originally, and here equals v. Okay. Else if used v, then I have to go down to, then answer plus equals 2, and I have to go down towards b. It's 2v u. At least I don't have to print out the path. Well, it's not that many. And then I have if is y if is y DFS to y dear y direction u, and I increase on answer by 1 only. Use plus n plus 1 0. I didn't even read the tree in. Okay. Three, 7, 2. Okay, that should be good. And then, should I look at G? Memory limit exceeded. All right. That's interesting. Huh. Memory limit exceeded on test 2. Okay, that doesn't really make sense. It's definitely not memory limit. So something else must be happening. Does one of the DFSs go on forever? Because I need to go from 1 to n. That might be causing some of the issue. Okay, yeah. Accepted. Should I check out G? Because this F wasn't that hard. I felt like that was pretty easy. And pancakes and spread them on end dishes. And spread. Huh? Huh. On her number from left to right, she put AI pancakes on the dish with the index I. Okay. Seeing the dish is flat, decided to bring order to the stacks and move some pancakes. In one move, he can shift one pancake from any dish to the closest one. That is, select a dish I and do one of the following operations. Move one pancake to the left or one pancake to the right. That sounds like some very like a classic problem. I move on from 5 to 3 and then 3 to 2, 4 to 2, and it's gonna be 3, 3, 3, 3, 3. Or 4, 3, 3, 3, 3. One interesting number is how many pancakes there are at the very first dish. The maximum number is all of them. The minimum number is m divided by n, rounded down or up some way. Here it's gonna be put the 4 there and put 2 pancakes from the 5 to the 1. Huh. That's an interesting problem. I think I'll solve that later because I just want to explain all of my solutions, and then I can upload it close to the end of the contest. I spent half the contest eating, so I'm not surprised that I'm a bit late. Well, problem A. In the pet store on sale there are A packs of dog food, B packs of cat food, and C packs of universal food. I have X dogs and Y cats. Is it possible that I can feed both my dogs and my cat? Well, I just need to look. So first I will use up all of the dog foods and the cat foods for the cats and the dogs respectively, because it's worth it for me to use up all the cat food, because the cat food can only feed cats, so I'll try to use up as much of that as possible. So I have after that y minus b cats left to be fed, and x minus a dogs left to be fed. Of course, if a is bigger than x, then I don't have -5 dogs to feed, I have 0 dogs. And I have the remaining dogs and cats, and I have to see if I can feed the remaining dogs and cats with C. And that's what I do here. I have the remaining dog food, remaining cat food, and if that's smaller than or equal to C, then it's possible. In problem B, we had to make an array increasing by performing a given operation. The given operation was we can divide any element of the array by 2. And we have to find the minimum number of operations to make it increasing, or print out -1 if it cannot be made increasing. Well, basically there's only really one way to make it increasing. I haven't proven this problem yet, so let's look at the last element. There's no reason to change the last element, because when we want to make it increasing, the last element should be as big as possible. And if I made the last element smaller, well then that could only make the situation worse, because it needs to be increasing. So I won't do anything with the last element. Then I have a next element, y. If y is smaller than x, then the same argument holds. I shouldn't perform an operation on y, because let's say I put y into y over 2, and by this the array will no longer be increasing. If it was like 4, 5, and 3, if I changed 4 into 2, well, after that it wouldn't be increasing, so I shouldn't do that. On the other hand, if the next element y is bigger than or equal to x, Well, then the only way I can make this array increasing is by turning y into y over 2 until y is smaller than x. I have to perform at least this many moves to make the array increasing, and after this property holds, we've already seen that it's not worth it to divide this element by 2 again. So we have to increase it at least this many times, and we have to increase it at most this many times. So we have a minimum, and we do this for all consecutive elements. Yeah. And if two elements have become 0 next to each other, after that they cannot be decreased, well then I cannot solve it. Okay, problem C. In this problem, there's a room with a painting, and some friends from 1 to n go into the room and then exit the room one by one. And after that, after this whole friends going in and out, the painting was stolen. And we have to find who could be the possible thief. To do this, we ask all of the friends a question whether the picture was in the room when they went into the room. And they respond either by yes, no, or they don't know. So 0, 1, and question mark. Of course, one of them is gonna lie, the thief. The thief can answer any of these. And we have to find how many people the possible thieves could be. So basically, in this problem, let's say this is the thief right here, we know that before the thief everyone was telling the truth, so they should all say that so let's say no one puts question marks. They should all say that the painting was in the room, the thief will lie, and all of the guys after it will say that the painting was not in the room. So this is what the thief's position would look like. It actually doesn't really matter if there are any question marks here or here. So basically the thief can be a position such that before the thief there are only ones or question marks, and after the thief there are only zeros and question marks. Because if there was a 0 and a 1, well, one of them must be lying, because we're assuming that the painting was stolen here, and if there's a 1 after it, well, then that person must be lying, so if this one cannot be a thief. We reach some sort of contradiction. So what I did is, for each position, I store whether this person can be a thief. Originally I say everyone's a thief. If there are only question marks and ones before this position, then it can be a thief. So I end it with 1 if there are only ones and question marks before it, and I end it with 1 if there are only question marks and zeros after it. So this guy will only be a thief if both of the conditions that I've discussed here hold. And then I just sum them up. I could probably do this with some function, but it's good enough. Okay, problem D. We have to So given a rooted tree, we have to split the tree into some paths, and these paths can only go from node to parent. That basically means we cannot have a path like this. Well, let's think about it, and we need to do this with the minimum number of paths. Let's see how many paths we need at least. Well, we need to have at least as many paths as there are leaves, because from a leaf, so for a leaf to be visited, we need to go from the leaf to its parent, and a leaf can only be visited by going through a path from its parent, and that doesn't really make sense. No, it's we definitely need as many paths as there are leaves. It's just that I cannot really think of a good way of explaining why that is. I guess the other way around it's easier to prove. So if we have one path beginning from each leaf, then we can solve it pretty easily. We just start from a leaf and go up as many nodes as possible, and we say all the nodes that we touched have been visited. Then I start from the next leaf, go up as many nodes as possible. So there it would be one node, here it's 3 nodes. Start from this leaf, go up as many nodes as possible, and it's 1. So that's the strategy if we start from all leaves. The reason we need at least, so I know that we need at most as many paths as there are number of leaves, because we can make an algorithm starting from leaves which solves the problem. Why do we need at least as many paths? Well, let's say there are less paths than there are the number of leaves. But then so each of these paths go from a node to a parent, and if there are only, let's say there are k leaves and k minus 1 distinct paths, and all the leaves, well, they form k node to parent combinations that will not be included in one path. So if I only have k minus 1 distinct paths chosen, there's gonna be exactly one leaf which hasn't been visited. Okay, so basically, not to overcomplicate things, what we do is I select the leaves, and from each leaf I go up as high as possible, and I store all the nodes which I visited, and then I print out the path. Okay, problem E. Here we were given some string. I think I have this problem written up somewhere. And what we can do is, let's look at an example, the CBA. What we can do is we select a letter, let's say C, and we turn all C's into B's. After this we can select, or let's say at first we select the letter B and turn all B's into A's. We can only turn it into the letter that is one lower than itself in the alphabet. In A we can turn into a Z, but that will not be useful in this problem. So let's say I do this, then it's going to be CAA, Then I select C and turn it into B. That will make it B, A. Select B and turn it into A. That will make it A. And what we need to do is, using at most k operations, find the lexicographically smallest string possible. First thing to notice is, after I've chosen the operations, it's always worth it to do the operations in order from largest to smallest. So let's say I have an operation where I turn B into A, I have an operation where I turn C into B, and I have an operation where I turn D into C. If I do it in this order, then the B's will be turned into A's, the C's to B's, and the D's to C's, which is not bad, because the string will definitely become lexicographically smaller. But if I do it this way, all the characters that are D or smaller will become A's. So it's always worth it to start from the largest. And after this, I just go through the string letter by letter and decrease the first letter as many times as I can. Meaning, I decrease it until I reach A or I run out of operations. And the way I know which letter is which, so I store what letter I've turned the current letter into so far. So let's say I have the first letter E, and I've already altered the first part of the string, and I'm at the letter E. And we see, first what I do, I have some operations left, 2 operations left. So first I turn E into A, B, C, D, E. So I first turn it into D. And with a disjoint set union, I store what the actual value of D is. So initially the actual value of D is D, but then later it could be that through some operations I've turned D into A. So if D has been turned into A, then I add E to that set of elements which have been turned into A. I actually probably don't need to use a disjoint set union here, but that's the way I found it the easiest. Here I go through the string, and while the current letter is not 0 or A, and I have an operation left, well then I'll unite the current and the current minus 1th letter, and by uniting I mean decrease the letter by 1. Because we need to find a lexicographical order, it's always optimal to minimize the first letter of the string, then the second letter, then the third. Because the first letter is the most significant letter. Yeah. And finally, problem F. Here I have actually explained my solution while I was thinking about it, but I'll explain it again. Maybe I'll draw a new one. So I am at house X and I have to reach house Y. I'll explain the problem as I draw this tree graph. I'm in a tree, have to reach Y. And I am also given some tasks to do in some of the nodes. Excuse me. So here I have a task, here I have a task, here I have a task. And let's generalize. In this subtree I have a task, in this subtree I don't have tasks, in this subtree I have a task, this subtree I have a task, here is a subtree where I don't have a task, and let's say here is a subtree without a task, and here is a subtree with a task. Okay. What I have to do is reach y from x by moving to adjacent nodes. And also I have to complete all of the tasks. So I need to also, through my path, or like walk along this tree, I have to go past all of the vertices with a 1. So here I could do something like I go down here, then I go down here, explore this subtree, go back up, down here, back up, down here, back up. Then I have to go all the way down here, back up, all the way down here, back up. And I'll go back up here, can go down here, back up, down to y, but first I go down and explore this subtree and down to y. So this is one possible path. I can make this a little better. And then I'll explain the solution. Basically, what I have to do is, let's do like a DFS sort of thinking. For each node, I'll store whether there's a 1 in its subtree and whether there's a y in its subtree, or whether y is in its subtree. So for each node, if there's a 1 in its subtree, I'll write 1 into it. So 1, 1. There's a 1 in this subtree, 1 in this subtree, 1 in this subtree, 1 in this subtree, 1 in this subtree. No 1, no 1, no 1. Let's put another node without the 1. And I also mark the nodes where there's a y in the subtree. So here, here, and here. And the way I solve this problem is I go through all the nodes that are children of the current node I'm at. If there's a node with a 1 in its subtree, well then I have to go down there, solve it for this subtree, and go back up. So this time I increase the answer by 2, plus I solve it for subtree and next, plus I solve it for this next node. And if the y is this way, then I'll just go down, and I'll always make sure that this is the node that I examine last, and then I just increase the answer by 1 plus subtree next, and this subtree function is going to be our DFS function. So here I go down, solve for this subtree, come back up, go down, solve for this subtree, come back up, go down, solve for this subtree, come back up, go down, and then go down, solve for this subtree, come back up. And at the end, I'll finish at y. Inductively, all of these subtrees have been solved optimally, and I always go towards y at the end. And I'll show my code for this. So I have used is whether I need to touch that node during my walk, and y in says whether there is a y in this subtree. I have these markers for used. Originally I read in the nodes, then I do DFS1, which just turns these values into like subtree aggregates, and then I have DFS2, which basically does what I've explained here. Is if there's a y in this subtree, well, I'll put it into last. I do that by turning this bool to 1, and then I'll do it last. Otherwise, if there's a used node in this subtree, then I'll increase answer by 2, and I'll go down that subtree. Yeah. Problem G, I'll solve problem G later. It looks quite interesting. I don't know. It looks like there's a. It's like a, I don't know, classic problem that I should know how to solve, but I haven't seen it, or I don't know yet. I didn't just read it and know exactly how to solve it, so I guess it might be harder. All right. I hope this video helped some of you, and thanks for watching.